Um, okay, our recording is now started. So welcome back, everyone. I'm Min-Soo Kang. I'm an assistant professor of School of Computing / Graduate School of Information Security at KAIST. So I am going to continue from where we left off last time. We actually finished the very basics of blockchain last week, and then we're gonna add something more onto that. So we call it advanced topics, but don't worry too much. It's not really a super advanced, more in-depth one. It's just a more of an emerging topics, overview of emerging topics. So we have two parts today. So part one will be taught by me. As I said, some advanced or emerging topics will be covered. And part two, Dr. Sam at Clayton Foundation. He's a director of Clayton Foundation, and he's going to tell us about how complicated it is to build a blockchain platform. So what I'm going to talk about is basically, it's a mixture of my own experience with blockchain projects and some of the readings and paper readings that there's knowledge that I've attained from papers. But the part two will be about really the hands-on experience. Sam has been building Clayton, large-scale blockchain projects. So we're gonna learn a lot of real experience from him. Okay, let me start. So I should recap of the blockchain 101 last week, and some students actually expressed concerns about it because some students and at the every time one of those anonymous student community saying that a blockchain 101 lecture was very hard to follow as I have zero background, and some actually, maybe I think it's another student even said that worried that whether he or she can actually survive in this course after taking this blockchain 101. And I was worried too. Maybe I scared you off too much unnecessarily, because as I said before, I mean, I actually mean it. So you don't have to worry too much about it. You can develop Web3 apps without becoming a blockchain guru. You don't have to understand the core of consensus algorithm to write a Web3 apps. You just need to understand some characteristics of these underlying blockchain systems. So if I give you an analogy, I mean, I'm not sure if it's a good, perfect analogy or not, but no analogy is perfect anyways. So you can think of the blockchain as a highway or the road system, and what you're gonna do is not to develop a road or build a road. You are going to build a vehicle that runs on top of the highway or road. And so basically you don't have to know everything about the road system itself, but when you're designing your car, you may want to know what road condition this car will be running on, right? I mean, if your target is a highway system, then you may want to have certain design criteria, or if you are trying to build, if you know that your road system is a bumpy road or muddy road even, then yeah, you may want to consider something in your car design. So that's the that's a level of information that I'm trying to deliver you, and I'm expecting you to have before you dive into this Web3 app lectures. Okay.
Professor Kang, can I add one more thing?
Yes.
So after midterm period, we will have two more extra lectures from Wansum Lim from Ethereum Foundation. So he will teach you the detail of Ethereum from 101. So you can understand how Ethereum works, and also you can learn cryptography from him. So don't worry about that. So you don't need to know the detail of blockchain technology and blockchain platform, but you will have more chance to learn the detail of blockchain. Okay.
Yeah, it's great. I mean, it's always great to hear from the people from the industry, and it's really good that we have many good speakers. So Yeah, don't worry too much. But it's good that it's good that you guys express your concerns. I mean, even in this anonymous platform, I mean, I do read those forums, anonymous student forums. Many professors do that, anyways. So yeah, please express your concerns directly to us in the Discord channel or even through this anonymous channel. So that helps. That helps. So, with that, I want to recap what is blockchain. So the short answer, abstract answer would be that blockchain provides coordination between many parties when there's no single trusted party. So that is the essence of blockchain. No trusted party. You don't want to trust any single person or single organization, but the algorithm and the protocol, and that is the source of trust that you enjoy, and that is really the key. And in order to fully understand what that really means, that we discussed this notion of consensus and consensus algorithms and why it's good and bad. That was it, really. So if you don't need a trusted third party, then I mean, if your trusted third party exists and you are willing to trust that entity, then there's no need for blockchain. So we've seen that Bitcoin was the very first one. That shows that a practical public append-only data structure is possible through replication and giving incentive to those participants or validators or miners. And as a result of it, or maybe a part of it, is the cryptocurrency. So that's what we have for Bitcoin. And Ethereum expanded the idea much wider. So now it becomes a blockchain computer, because a fully programmable computer can run on top of this blockchain. So that actually enables all the Web3 and the apps. And this also provides composability, meaning that you can add multiple applications that call each other for different, as long as they are actually following the protocol. So in the recent, so this is what we're gonna more look at. I mean, this time range is what we're gonna look at in the first part of today's lecture. So Bitcoin, if you just summarize as a state transition system, it looks like this. At every block interval, the world state of Bitcoin is determined in the form of block or set of transactions, and they are just saying that, hey, look at this, these are the number of coins that we haven't spent yet. So that is really it. And then if there exists a number of transactions that try to spend some of the coins that haven't spent yet, that becomes the input, and that makes an update to the system, and then as a result that becomes a next block. So since blocks are, tied together and chained together all the way back to the very first block, so we call it a blockchain. And if you look at the history of a blockchain, I mean, if you follow the chains of those unspent transactions, then you can actually see that how cryptocurrency, in this case coin, has been spent for whom and for what. And that is really Bitcoin. And Ethereum is now it is also a state transition system, but it can actually execute an entire program. So we have seen this figure. At the top, we have a blockchain. On the left-hand side, towards the right-hand side, the time progresses. So once you actually upload your program and the initial state of the program, and then send it to a blockchain, and they are actually uploaded to the blockchain. Uploaded to the blockchain, meaning that the code and the initial state is actually written in a block in this blockchain, and that block is accepted and confirmed with very high probability. So with very high probability, close to 1, that contents will be there unmodified forever. Okay, so that is it. That's that's how you install or upload your program. And then whenever there exists any transaction that tries to change the state of this blockchain, as we have seen in Bitcoin, it not only changes the the monetary value in each wallet or in each account, it also provides inputs to that program code. So then, the miners or the validators of Ethereum should actually execute that program code, the green piece, using this transaction one as an input based on the state 0 that it has known for this program. So then as a result, it becomes a state 1. The program code stays there, right? I mean, it's just following the traditional computer model. And that's how it progresses, and that's how the program is executed on the blockchain. So whenever someone says that, hey, the program runs on the blockchain, he or she means this. Okay, and for this program to run, input has to be provided, and that input is a transaction, and transaction has to be uploaded in the blockchain, the main chain. And this was just an example that shows a very simple but vivid example of sending a transaction, and that transaction is executed and changes the state of a Ethereum network. And so at the last part of last lecture, we have discussed the one big change that Ethereum has experienced last year. And it was actually a big deal for Ethereum community because there used to be always a proof of work, some kind of mining and burning fossil fuels, but not anymore. After the merge, there is no such mining necessary for Ethereum. So the amount of electricity usage for Ethereum is down to a handful of percentages. I think I'm getting a question. That's good. Then how can we change our program code if we want to change? So that's a really very good question. So one simple answer to that is that you cannot change the program code, and that is the reason that vetting your program, basically your piece of code should be reviewed very, very carefully, and you need to use many tools to make sure that there's no bug in your program code. So that is a basic answer. And why? Because once it's written on the blockchain, it shouldn't be modified. And there has been some proposals that suggest that, hey, I mean, if the majority of, let's say, operators or miners agree that certain thing on the blockchain should be modified, then shouldn't we allow that? So there has been some variants of blockchains that actually allows change of contents even after several blocks has passed. If the majority agrees that we need to change that a few days ago, then they allow. So there's certain blockchains that allows that. Or you can actually allow the program to evolve from one state to other state using fancy tools that updates your program in Ethereum. I think that can be discussed later when Ethereum people comes and discuss about that later.
Can I add one answer?
Yeah, sure.
So,
please.
You will learn how to upgrade your smart contract a few weeks later. There is a tactic to upgrade your smart contract. Actually, you cannot modify your own program. Instead, you can make your proxy smart contract as a front end, as a front smart contract, and then this proxy smart contract connected to real smart contract. And then when you upgrade your smart contract, actually you have to put another smart contract, and then you have to modify the connection to to new smart contract. So you will learn this kind of tactic a few weeks later.
Yeah, that's exactly right. Yeah, thanks for that. You know, the comments.
Okay.
So so in a nutshell, from the blockchain's perspective, it is true that you cannot modify anything, but from the smart contracts programming skills and those tool sets point of view, yes, you can update it. Okay, cool. Yeah, thanks for the question, and I think this is great. We have a open discussion during this class. So yes, so that was what we have discussed, and what we have seen is this. In blockchain, there are many good properties, and which can be summarized as this. Safety. All honest participants have the same data. If you are just benign, if you decide to follow the protocol, do nothing bad, then you will see the same data, which is extremely important. Otherwise, you'll be the victim of some sort of attack. Persistence, once something is added, data can never be removed. So that's what we have discussed. Liveness, honest participants can add new transactions. So this is about related to the availability, and we use the term dynamic availability in the sense that some part of maybe even half of the miners may go offline, but still network should proceed. So and that is one thing about liveness. And another thing is the censorship resistance. This is actually an important topic, and this was originally designed. Built-in scheme, built-in feature in blockchain from day zero. Why? Because we want to. The early days of a blockchain, people, they wanted to create a sort of a financial system, alternative financial system that can avoid censorships and government interventions. So it was very important, meaning that if someone wants to make a transaction, that transaction must be included. So there shouldn't be any middleman or middle guy that looks at this transaction and say, hey, you cannot do this. This is bad. You cannot do this. So that kind of censorship should be prevented. And underlying blockchain provides that. Why? I think we have seen just very briefly, there's a network of peer-to-peer nodes, 10,000 or even more are fully disconnected to each other, well connected. So it's very hard to censor transactions in typical blockchains, which is good. So, but it's not there yet, because we have some problems. Throughput. So what about throughput? Latency and cost. So lots of transactions per unit time should be good, right? If we can handle like thousands, and I think every time people are talking about throughput, transaction per second, they show some variance of this slide. I just grabbed some random thing from from Google, but you have seen this before, right? So Bitcoin and Ethereum is far from this Visa kind of a transaction. So how can we actually provide this level of throughput? Latency, how can we confirm a transaction in 1 second? So anything that beyond 1 second can be considered slow. Imagine you build a Web3 cool application later this semester, and then you're experiencing too long latency, then you'll be discouraged. And so you need to understand the limitations of blockchain that you are trying to use. And the cost, making transactions can be too expensive. Depending on the applications, but it can be considered too expensive for certain applications, and actually many applications. So we want to solve this. Then since you roughly know what is blockchain, now you can probably say that, hey, can't we simply increase the number of transactions per block? meaning that, maybe here or there. So every 12 seconds or every 10 minutes in Bitcoin, 12 seconds in Ethereum, they are creating blocks, boom, 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 new blocks, and they're connected to each other. And in each block, there exist many transactions, and right. So can we just increase it further, like 10 times larger or even 1,000 times larger? If we make Ethereum blocks 1,000 times larger, then yes, we can actually compete with Visa now. So what is the problem? What's the problem of having larger blocks, 1,000 times larger blocks? If you have followed last week's lecture, then you can guess what's the reason. Yeah, so Nurli Khan just mentioned load on miners. Yes, miners now have to process too many transactions. So that's one. And also it's gonna overload the network, because it's not, we're not talking about a single or 5 nodes on the internet. We're talking about 10,000, even more nodes on the internet, and they need to, exchange those block information. Otherwise, it's going to be messy. Not only messy, it's not going to be a blockchain. Every miner should have the same view, same set of information. So things has to be exchanged very quickly. How large? 10,000 ish number of networks. I mean, if you think about it, that's amazing, large scale network. So if you just increase the blocks, then the time that's new block delivers to the most of the node in the over the internet is going to increase. And also the time to verify all the transactions and actually run the smart contract will also increase. So it's not going to really work. So the things that you should really remember is something like this. You can't really complain too much about Ethereum. If you have any complaints, you should really understand why is this sucks in some sense. Okay, then I think in the next, let's say 40 minutes, I am going to spend most of my time on this topic, scaling blockchains. How can we really scale up the blockchain? Because we want to increase the throughput, we want to shorten the latency, we want to reduce the cost. So all that can be somehow related to the scaling up idea of blockchains. Can someone tell me your basic intuitions? You cannot throw out any jargons, blockchain jargons, if you know something. Tell me something, how can we do that? I mean, so one first idea got rejected, just increase the block size, got killed immediately. Is there any other approach that you can come up with? Okay, someone is using jargons, sharding, I think it's considered jargon. Okay, TA Jong Mingyu said compressing data. Yes, compressing data makes sense, right? If at least the blockchain, requires us to write everything on the chain so that anyone can verify that. So if you can compress that, yes, it can probably help. So SegWit, sharding, make multiple chains. Oh, Dongyu said make multiple chains. Yeah, that actually makes sense. If you want to scale up the blockchains, then why don't you make one chain and second chain and maybe chain number 1,000? Then we are scaling this up 1,000 times, right? I mean, yeah, thousands. What is that? 1,000 chains are running in parallel. And of course, there's a problem, if there's multiple such chains, and how can you actually move around money from one chain to another chain? Otherwise, it's going to be different silo, separate blockchains. It's not going to be very useful. So, but that's a good approach, but it's not sufficient. Probably layer 2 could help, but what is layer 2? Let's not use jargon here. Mingyu also said that using superfast machines. Yes, superfast machines will help, but network becomes a bottleneck anyways. So our current internet cannot handle, 1,000 times larger blocks, period. It cannot. Yeah, so can someone add more feedback? Any random ideas? Okay, that's good. Oh, yeah. Chamin said changing transaction per block according to the number of transactions per time. So okay, that's a good approach. I think what Chamin is trying to say is probably that instead of packing too many in single block, maybe we can send blocks more frequently. Then we can send just slightly more transactions, pack slightly more transactions into a single block. So each block is not that large, but we can send more blocks more frequently. But as we have seen last week, if you actually shorten the block distance, the average time between blocks, and you squeeze it too much, then you will start to have a problem of partitioning and selfish mining and all that, because the time for each mining process, average mining process, and the network delay, when they become similar, then attacks are becoming relatively much easier. So attacks meaning you can actually break the consensus. So it's all related, and it's actually quite hard. It is actually. So it is unfair for me to ask this question to you guys and expect you to come up with super cool solutions in 5 minutes, because this topic has been studied in the last 6 or 7 years, and the brightest minds in this space has been spending hours and hours to do this. So we're gonna actually look at some of these cool ideas today, and so that at the end of this maybe next 30 minutes you'll be able to grasp the high level idea of how we can actually scale the blockchains. So the first idea is sharding. Someone actually said it. It actually means that we are parallelizing the blockchain network. And someone also said that we can run multiple blockchains. I mean, it's roughly that, but it's slightly different from that. So we will see what it is. And another idea is payment channel. So in the payment channel, it's actually the starting point of the notion of layer 2, meaning that whatever we have in the blockchain, Ethereum blockchain, Bitcoin, that becomes a foundational layer, layer 1. That's a default layer. And here we're building on top of that something on top of Bitcoin, blockchain. So sometimes we call it layer 2 or L2. But it's a payment channel is the very first version of very first implementation and design of layer 2 that tries not to touch blockchain as much as possible. It means that it touches the blockchain, it writes something and reads something from the blockchain, which is very expensive to deal with. It's slow and expensive, right? So it tries to avoid it as much as possible. That's the idea. It may sound weird, but that really is the idea, and it actually works. And the more recent idea is rollups. And rollup here, we are writing only the summary at a very high level. We're writing only the summary of transactions and contract executions to the blockchain. So we are actually writing things into the blockchains for every executions, but only the high level summary and the proof. We'll see what it is. So all these use different strategies, very different strategies actually, to scale up the blockchains. And the layer 2 payment channel and rollups, they are called layer 2 approaches. Why? Because they're trying to do something outside of the main blockchain. They are interacting with the main blockchain, but they're doing most of their job outside of the blockchain, or sometimes we call it off-chain operations. Okay. So people are talking about, I mean, you may hear about those terms, sharding, payment channels, rollups, lightning, but what I want you to understand is the main concept. Those concepts that are highlighted, parallelize it, try not to touch blockchain as much as possible, and write only the summary of it. Those high level insights are more important, I think. So let's look at one by one. I should actually mention that some of the slides that you will see from now on are borrowed from my student, Jaeyeon Ha. He's a graduate student here at KAIST. So I ask his permission. So what is sharding and why it's needed? So in general, sharding is actually a terminology used in database community, and it's about method of splitting and storing single data set into multiple databases, because single data set is too large, so you want to shard it and in multiple database. In blockchain, people try to use this idea of sharding in blockchain in around 2016, and by distributing the set of transactions to partitioned committees and process block in a parallel way. So remember the parallelize, that was the terminology. So let's quickly see what it is. But before we do that, let's look at this diagram that nicely illustrates the limitations and opportunities of new ideas. The x-axis of this is a number of nodes in the network. Y-axis is a TPS, transaction per second. You may see TPS a lot. TPS means throughput, transactions per second. So we have seen the Nakamoto-based consensus models, Bitcoin in an early version of Ethereum, right? It has been always very slow, low TPS, and this TPS doesn't increase as the number of nodes in the network increases. Why? Because the block size is the same, and the block time difference is the same, and it cannot really increase as the number of nodes in the network increase. So you may actually feel a little bit weird, puzzled, because in many P2P applications like BitTorrent or Napster, early days of P2P, the main premise of their peer-to-peer network is that as the number of nodes increases, the capacity of the network also increases, right? That's the premise. But in this Nakamoto consensus, as the number of nodes increases, it's the same. Performance is the same. The reason is that the database is not distributed. Every node in the system has to have the same replica of the data. And that's if from the early days of a peer-to-peer network point of view, that's very weird. That's the reason that TPS is very slow. So the natural idea is that why don't we just shard it? Split this gigantic database, and then so that a small group of users can handle a small group of transactions. That's the sharding idea. And that is actually that can be found in the early days of peer-to-peer network design. Small number of things are distributed, so that as the number of nodes increases from the left to right, you can expect better performance. That is what sharding is trying to do. So in this sharding, what people want to do is to increase the transaction rate almost linearly with mining power, meaning the number of miners in the network. So for our discussion is based on the following paper down there. A secure sharding protocol for open blockchains appeared at ACM CCS 2016, which was one of the earliest, I think it was the earliest academic paper that shows that sharding is applicable to open blockchains. So we're gonna follow the logics here, but some other sharding protocols can be different from this. They are actually different from this. We may have some time to discuss. Yeah, probably not. But so do note that we're following this paper So you may see some slight differences or many differences from this early inception of sharding idea. So in this paper, they call it Elastico, and that was the name of the protocol. And then they actually, they got a startup and with the project name Zilliqa. There are 4 steps. One step is to create small committees, because now, a small group of users have to has to be responsible for smaller data sets, not the entire data set, for consensus. So that is the number 1, we need to form a committee. And number 2, within this committee, they need to come up with, we need to form a committee. Okay. Number 3 is that they need to come up with a consensus within the committee. And number 4, there must be a harmonization process, if you will, that can generate final consensus final block that combines everything and then broadcast to everyone. So this, you see the main idea, making a consensus among like many others is very hard. Now you divide this consensus problem into a smaller pieces, so smaller groups solve that problem, and then after that they gather together to create a large block. For the committee formation, because we want to avoid any trusted third party, it can based on the proof of work. Everyone is just try to mine, but much easier problem than just mining a Bitcoin block. And then based on the result of their solution, proof of work solution, they can actually form different committees, in a fully decentralized manner. So if your solution is something like this, then which ends in 1, then you go to committee 2. If your someone's solution ends in 0, then that node goes to committee 1. And it can happen automatically and fully decentralized manner. And in order to make it slightly more effective, basically they introduced the notion of directory committees, which is not that important for the purpose of this discussion, so I'm gonna really skip. So after they form multiple committees now should be handling some transactions, but not all. So let's say there are many transactions, as you can see at the bottom, in the middle bottom part. Then transaction IDs may have may start with 1, then they all go to committee 2. So committee 2, the nodes in the committee 2 should actually run a consensus algorithm for those transactions. So it's really divide and conquer, and you divide the number of set of transactions that you need to handle and then conquer it in different committees, which are formed in a fully decentralized manner. So for this consensus algorithm, you can run any variants of BFT protocol, which was not the scope of last lecture, but BFT protocol is a highly efficient consensus algorithm. I think this is just enough to say this for this lecture, but it's a highly effective, efficient consensus algorithm, but it works for only a small number of members, like 30 or 40, maximum 100. So in practice, maximum 100 is roughly the maximum of typical BFT protocols for them to create a consensus very efficiently, like in a sub-second or a second. And then, when they agree on a set of transactions, then that becomes a shard, the output shard from this committee. So it can be very fast and it can be confirmed. So it's finalized at every, let's say, second. And after that, all this data block are going to the final committee where they actually make the final consensus based on these confirmed finalized blocks. And then, they agree on the set of valid headers on the data blocks, which will give us the final block. So again, divide and conquer, and then combine all that once to create the final block, which will be very big, and then that will be sent to all the miners in the system. Yeah. So the results shows that if you are increasing the network size, the number of nodes, or the number of miners, then you can expect more number of blocks that you can actually handle in a given time. So so you can actually expect better scalability. So we've seen this sharding idea, but it has some, weaknesses, I would say. In the example that we have seen, like Elastico, that was the very early version of sharding, there must be a cross-shard consensus at the end of this cycle, because smaller pieces, smaller committees, they actually worked on their own consensus, smaller sizes. Now, the bigger size, entire transactions must achieve this consensus for cross-shard, through cross-shard consensus, which is not, magically done. So that's a additional, thing. And in some other sharding protocols, unlike Elastico, some other sharding protocols, they actually form a smaller committees, and then smaller committees come up, maintains different chains. So in the Elastico, your chain actually, you're maintaining a single chain, but every consensus cycle, you are splitting them into, incoming transactions are split it. But in some other transaction, sharding, they have parallel shards. And every time a new transaction that involves multiple transactions or multiple accounts in different shards, you need to run a cross-shard consensus for each transactions. So when that happens, you can actually hurt the composability of your transactions and your blockchain, because you have to actually talk to multiple shards, and there's no the performance and issues are there, and also there are some security risks that were reported when cross shards are happen. Something can happen. So there are some limitations on sharding. Okay. The second idea of scaling blockchain is payment channel. By the way, if you have any questions, then let me know. Let us know. Yeah, let us know. There are many people who can actually answer to your questions. That's good. So the second part is the payment channel. Here, people try not to touch the blockchain as much as possible. They touch the blockchain only when it's so necessary. So what does that mean? So the layer one, as you can see here, is the main blockchain, where you are writing something up, and then that becomes a permanent entry in this chained blockchain. Okay. So we say, some transactions are on-chain, meaning that they are written in the main chain, or now we call it layer one. Okay. So the layer one, main chain, on-chain, they're all the same thing. So I think one of the obstacles in understanding and following up what's happening in blockchain scene is to get familiar with those terminologies. If you're a newcomer, then you will see so many different terminologies which actually mean the same thing. So this is one of those things. So, okay, anyways, so Alice and Bob in this case wants to make some payments to each other. Let's say, Alice wants to pay Bob $1, Bob pay back $2 tomorrow, and something like that. They want to have this channel, and they want to make micro payments, those small money. If you want to send, $1, and you have to spend $2 for fee, because you need to send your transaction through Ethereum, then it doesn't make sense at all, and the fee fluctuates. So you don't want to do that. So and also you have to wait for, a couple of minutes. So in order to avoid that, you can actually write a transaction, Alice and Bob together, to lock up some money for a channel. And then based on that channel, Alice and Bob now exchange signed transactions between these two, only these two, but without actually sending it to the blockchain. So that is what's happening in layer 2. And the Lightning Network is one of the earliest such payment channel that showed up in Bitcoin. So using Lightning Network, you can actually make payments to anyone on the Lightning Network, and very fast. It's very fast, in a few seconds, if I'm not mistaken, few seconds delay, and it's very easy to use. There are some limitations which we'll discuss later, but it's actually one of the standard fast transaction micropayment services that you can use today. It's been around for several years. So how is it possible? I actually unfortunately have just a couple of slides there. So you can think of it this way, when Alice and Bob signs a transaction, they both sign it. As you can see, A and B both sign these transactions and then written on the chain. And it makes sense because both are signed. These signature from A means that X BTC, Bitcoin, comes from the Alice at a wallet. It actually verifies that Alice can actually do that. Bob's sign signature also does that too. So it is locked up in this chain. And after that, Alice and Bob, when they make payments to them, they adjust the amount of X and Y just a little bit. Let's say X become X minus 1, Y plus 1, and that becomes a transaction. And then that, if Alice is sending that transaction to Bob with Bob's signature left open, then it means that Alice is sending 1 Bitcoin to Bob. Because as soon as Bob signs the transaction and upload it to the chain, then Bob can actually cash out this $1, because Bob earlier invested Y BTC, but now Bob cash out Y plus 1 BTC. So, but Bob does not do that because Bob does not want to close this channel yet. Because once this channel is open, then Bob and Alice can send and receive such a micro payment. I mean, 1 BTC is not micro, but any amount of coin between Alice and Bob, as long as it is behind the limit which is defined by X and Y, the initial like investment between Alice and Bob. So they can make many such not completely yet signed transactions between A and B, and as a means to make micropayments to each other. So whenever they are done and they want to close this deal, and they can actually close this, close this channel by making a closing payment to the chain. That's the only expensive part. So opening a chain and closing a chain, these are the two expensive parts and very slow part. But everything in between Alice and Bob, by making micropayment channels, they're all very fast, and they are cheap. I mean, they're also free between Alice and Bob. And one problem of this, I mean, this is so cool, but one problem is that if Alice wants to, send some payment to Carol, Alice has to create this channel with Carol. And if there are only Bob and Carol, Alice can do that, but Alice should at the end of the day, should make too many channels to many of them, and which is bad. So that's why the Lightning Network, designed. That's why Lightning Network designed a network of such payment channels, so that Alice can find a route to Carol to send one micropayment through Bob, so that Bob can actually send this tiny money to Carol. I have one question from Nurlikan. Does that mean that the worst case scenario is that they open and close the channel for only one micropayment channel? Yes, as you said, Nurlikan, that would be the worst case. You open a channel, very slow, expensive, send one micropayment and then close it. Again, expensive and slow. So there's no value in it. So if you want to do that, then you just want to send one coin and that's it, through this on-chain, making an on-chain transaction, or Ethereum or blockchain Bitcoin transaction. So if you want to use it wisely, you open it and then use it for payment channel for a long enough time, for many transactions, and then close it when you really think that you don't need it anymore. So let's say Alice and Bob let's go back to this example. Alice and Bob, invested, 10 Bitcoins each other, and Bob and Carol also invested 10 to each other. Then Alice can send one tiny micropayment to Bob, and Bob can also send that tiny micropayment to Carol. So then Bob received one micropayment from Alice and spent one micropayment to Carol. So Bob does not lose anything, but provide this service to Alice and Carol. So Alice effectively sends that tiny coin to Carol. Everyone's happy, but Bob is not that happy because Bob is not making any money. So in practice, Bob is actually sending a slightly lower value to Carol so that he can take some cuts of it, like a fee, but that cut is can be much lower than the Ethereum fees or Bitcoin fees, because you're not actually running a expensive consensus, but all you are providing is just a routing service, and that's it. So one problem is that maybe Alice sends a one micropayment channel to Bob in the hope that Bob will actually forward almost the same amount to Carol, but how Alice can trust Bob, right? Bob can just take away money and then forget about it, right? So in order to handle that, there's a very simple trick called hash time lock commitment, right? So basically that forces that enables Alice to make a transaction to Bob with some condition, and Bob also sending another transaction to Carol with some condition, and then that condition can be met when Carol reveals certain information. Carol reveals some information which is hidden to Bob and Bob to Alice. So considering all the incentives that Bob, and especially Bob, can receive, this will work, economically sound procedure. So in the payment channel like Lightning Network, there exist many nodes like Bob who will be sitting there and willing to receive funds and then send it to others very quickly with a very tiny cuts of the transactions. So that's how payment channel works, and which works pretty well. But there are some limitations in payment channels as well. First one, user has to lock up their own assets. So let's say I'm Alice, and it's good news that I don't have to make payment channel to like any random people, but only to Bob, who is willing to provide this routing services. By the way, you can actually have multi-hops. Alice send Bob coin to Bob, and Bob is sending coin to Carol, and Carol is sending to David, and Alice is sending coin to David, something like that. Multiple hops are allowed. Not only allowed, it is it is needed actually, you know, in order to find the route. Yeah, but in any case, at least as an end user, I need to lock up some money when I'm making a channel with Bob. So, you know, I just want to send $1, but I have to make a, you know, lock up some money, you know, $1,000 there to create a channel. So that's not only inconvenience, it's a loss of opportunity, right? So and it has no value except for just, you know, having a channel. And also, it is mainly designed for payments, but not for contracts. So all you see is a payment, right? Sending money, receiving money. But Ethereum is not only a payment, it's a world computer. So it's not that ideal from that sense. So yeah, it's 5. I think I'm gonna use 15 more minutes. So the very last idea is what we call rollup, and this is actually more recent, and you know, it got attract more attentions, I would say, in the recent years. So people are excited about this rollup because you can do a lot of things without having many limitations that we have seen. So for this rollup, the idea, I mean, discussion of this rollup, I'm gonna use this paper Arbitrum, which was presented at one of the top places in computer security in 2018. So you know, you may actually listen to my lecture and then see some of other projects, even Arbitrum itself, then find some differences. You know, that's not my fault. You know, this projects are changing so quickly, and it's very hard to keep up with all the, you know, recent changes. So I decided to just go back to the one of this earlier original, you know, inception of this idea from this paper, and then, you know, stick to this. Okay. So blockchain layer one layer one is that, oh, by the way, I should mention that from now on for rollup, I actually have borrowed some slides from Professor Dan Boneh at Stanford. So yeah, layer one blockchain. Now you know that what we mean by layer one. Layer one means Ethereum blockchain, I mean Bitcoin, that we know. I mean, mostly Ethereum in these examples, and you know, roughly about 15 transactions per second. So whenever you're making transactions, that creates the change of world state of Ethereum, and this is how you know, progresses the world state of Ethereum. And we know this, but there are a number of I mean, limitation in the number of transactions per second. So one idea, rollup idea, is that why don't we batch many transactions into one? So basically, you know, many Alice and Bob and Carol is sending their transactions not directly to the Ethereum itself, but to a rollup coordinator. So there's a coordinator, you know, fancy machine here that receives those transactions, and you know, and then update the Alice balance and Bob's balance based on this transaction. So this is what the coordinator is basically, essentially, is doing what the Ethereum validators or the miners used to do. It updates the I mean, the states of this Alice and Bob's and Carol's of the, accounts based on these transactions, and then you kind of compress it by taking the only necessary things, I would say, and then provide some um, Merkle roots of it for basic integrity, and then send it to the blockchain. So basically, you add you know, transaction list. Maybe, you know, Alice is sending some money to Bob and something like that, without sending all the proof or signatures that comes along with it. You know, signatures has a much bigger size in general. So if you are removing those transactions, I mean, signatures, then the size of aggregate that you are sending up to this layer one is much smaller than just simple aggregation of all the transactions, which means that you can actually enjoy easily 100x speed up in transactions, because hundreds of transactions can be rolled up into a single transaction in terms of size. So then that's a cool idea, right? Now we can, just by adding a coordinator in the middle, you now have 100x scalability, which is cool. What is the problem? There are a number of problems. So what if this coordinator is dishonest? First of all, if you see this service, what you should think immediately is that, hold on, there's a problem. There's only one coordinator. Isn't that everything that we have done in Ethereum, in designing blockchain? We try to decentralize everything and try to not trust any single party and distribute the responsibility. That's what we have been doing there. But when it comes to just sending transactions and summarizing them up and then uploading to the blockchain, we're relying on a single coordinator. It sounds not right. It should look something weird, actually. It is actually a weird idea. So one problem is that from that angle is that coordinator can be dishonest. If coordinator is dishonest, then it can actually receive these transactions and do something else, execute in a slightly different manner so that we can actually benefit from it. So you can effectively steal funds from this roll-up contract, send the money to the coordinator itself instead of going to Carol. It can also issue fake transactions on behalf of users. You can exploit the opportunity there. So that is one problem. And another problem would be that, what if coordinator stops providing service? If the coordinator stops it and then dies there, then what happens after that? So problem one is more is receive more attention for now, at least. So let's see what how people is handling this problem one. That is, what if coordinator or coordinators are dishonest? So the idea one is that we can probably let the multiple coordinators, we allow multiple coordinators, first of all, and then let them disagree and then present a proof of fraud when there's any disagreement. So if all the coordinators output the same contract execution, then they form a unanimous agreement, and then L1 chain processes it immediately. Let me see if I have an animation because it's too many words. Okay, I don't have an animation for this optimistic rollup. Let me use just this. So let's say, in this figure, we have only one coordinator who determines everything, which is not so ideal. So let's say we have a multiple coordinators, use your imagination to that, and then there are multiple coordinators, and then Alice and Bob and Carol, they are sending their transactions to not only this coordinator, but another coordinator or multiple coordinators, okay? And then they process it, and then they talk to each other. And if they all agree on the output state of processing transaction A and B and C, then they sign it all together and then send it to the blockchain. And then, if the blockchain sees that, Ethereum sees that all three coordinators agree, then they just accept it. Okay, so that's a basic level of trust. What is that? If there's any one honest coordinator exists there, then that unanimous agreement won't happen, because there will be some guy who will say that, hey, something's wrong, I cannot agree with this, right? Then it's going to then the worst case scenario won't happen at least. So what if someone disagree with some other coordinator's operation? Then they can actually make a challenge. And whenever challenges happens, then now we are going through this proof period, where the two or more coordinators should come up with a succinct, very concise proof that can be presented to the Ethereum blockchain and then can be verified so that liar can be detected. So either the challenger or the original coordinator can be revealed as a liar who did something wrong, and then those who did something wrong will be punished. How they are punished? So if there's liar stake will be slashed. So one thing that is not clearly explained here is that the coordinators for this rollup idea has to stake up some of their assets, maybe pay a few ethers there to become a coordinator. And if their dishonest behavior is detected, it should be detected because there will be challenge period, then they got punished. They lost some of their shares. So, together this economic incentive or disincentive and deterrence and the dispute resolution mechanism, we can actually run this rollup pretty safely, because when something goes wrong, we will notice this. So this is why we call it optimistic rollup, because rollup is very fast in most optimistic cases where everyone unanimously agree on the output of those transactions. But in a non-optimistic case, it can actually take some time, because when dispute happens, dispute resolution period can take roughly about 7 days, just to give some time for users to take a look and then review their results. So that's really the idea. Many of the things are happening outside of this L1 chain. That's why it's called L2 scaling up idea. And another idea is to provide a better proof for the results that we are putting up into the layer 1. So let's say, okay, so I skipped this one. So idea 2 is that we let the coordinators to provide proof of validity. So in the previous example, coordinators provide just a transaction list and then send the output result. And then it is same as saying like that, hey, I've calculated all of this and trust me, this is fine. We all agree that, okay? If there's any disagreement, okay, we're gonna fix it up. But here, in this coordinator, it provides the proof of validity of all the transactions here, A and B, and then it provides not only the updated state root and the transaction list, but also the proof of valid transactions. It provides the proof that all the transactions are actually valid. And in the L1 blockchain, in like Ethereum, in the rollup contract, that it's a bridging between L1 and L2, it accepts a new root only if the proof is actually verified. And verification of a proof should be very fast and efficient. And that is succinct proof actually proves that a batch of hundreds of TX is valid. So like I said, it has to be short and fast to verify, and that's why it can actually make this. It can actually compress many of the transactions into one while not bothering this L1 too much. Otherwise, L1 can be slower, and it takes more time to verify this, and burning too many gases, and that's not going to really work. So that's what we call I don't have this name, but this is called ZK rollup, because the main tool, cryptographic tool that is used for creating this proof, validity proof, is a ZK snark, and that makes this very short and efficient proof that makes this rollup very effective. So the end result of this is that rollup contract on L1 ensures that coordinator cannot cheat. So it's not about, so we don't have to do this dispute resolution at all, because if coordinator cheats, then the L1 main chain will be able to detect it immediately. So there's no like, interactive protocol between these coordinators. One downside of this is that creating this, ZK snark proof is costly. It's still expensive. So reducing the time for this creating a validity proof is really the one key research, research opportunity. So there's another problem in this rollup. Let me just skip this. Oh yeah, I actually wanted to skip it. Anyways, so that's not really all. So we have seen three ideas. What is that? Sharding, payment channels, and rollups. There are many remaining issues. Sharding and payment channel. We have already seen those limitations, and rollups. This technology as a whole has to go through some more phases to see for us to see a mature version of it. And the censorship is another problem in rollups because, as we've seen before, in either ZK or optimistic rollup, there exists a small number of coordinators anyway. I mean, if we allow a large number of coordinators, then we would have a consensus layer again in layer 2, which doesn't make any sense. So, but small number of coordinators, then there's always a chance for censorship. Small number of coordinators, they can just collude, or any of them actually can do some censorship. So censorship in general, it can be a problem. And people are talking about L3 that runs on top of L2. So the main point here is that this scaling up technology of blockchain is clearly the very important issues in blockchain scene and blockchain technology for Web3 as well, because it's all related and it's changing very fast, and new things, new ideas, and new innovations comes up very quickly. So that's, I think, the end of my overview lecture on more advanced topics in blockchain. If you have any questions, please let us know now. Otherwise, we can have a short break, I guess 5-minute break, and then I will give this microphone to Sam, who should be here with us now. So yeah, any questions?
Actually, we can have a 10 minutes break
Oh,
because
10-minute break.
we will start at 30.
That's good. That's good. Yeah.
Mhm.
So 10-minute break. Then let me wait 15 more seconds. See if there's any questions.
As a one more information, we already prepared off-site seminars about these advanced issues. So some mentors will cover GK rollup, or some mentors will teach you some specific platform of L2 like StockNet, so you can learn a lot of things with offsite seminar. Actually, this seminar will be held in KAIST, will be at KAIST as an offline seminar, and then this seminar will be given in English, so any foreign students can participate in this offsite seminar.
That's really good. That's really good, really. I mean, because as I gave you an overview lecture to everyone, like, this is really an overview, and if you can follow up to this point, which is not that difficult, then now you can actually listen to and learn many good things, cool things, and recent things, and ongoing projects from these people from industry, and this is moving very, very fast. A couple of months, then many changes are there. So I also very look forward to seeing them and then listening to their talks, and I will also be there. So I hope many people will be there as well. Okay. Okay. Then I guess we can have 10-minute break, and I'll see you at 5:30, and Sam will welcome you.